Hey everybody, so here's some introduction to 5.2 and what we're going to be working with here. Where'd my mouse go? There it is. All right. In 5.2, we're going to start talking about polynomials. The word poly means many, and nomial is going to mean terms. So this is an equation with many terms. They're going to have x's with different exponents, but the key idea is that we have x's that have whole number exponents, and then they have coefficients in front of them, or numbers in front. An example of that would be like y equals 3x to the fourth plus 2x cubed minus 3x plus, say, 5. That's an example of a polynomial. Now these polynomials also have certain curves or shapes to them that are somewhat predictable. There's some information that we won't always know right up front, but there is some information that we will know at face value. And so we're going to talk about how do we do some substitutions into these, but also what do we know about their general shape of their graphs or their curves. That's just a general statement about them. So a couple of things. First things first. In the first part of the assignment, we're going to be working on finding what's called the leading coefficient and the degree of a polynomial. So whenever we have a polynomial like this, we always have to first start by finding the highest exponent. Now it's nice when they're written in order, and they won't always be written in order, but in this case they are. Our degree for this polynomial would be 4, okay? And our leading coefficient takes me longer to write than say, leading coefficient would be the number that's the coefficient of that x term. And since we're talking about x to the fourth, we look at its number in front, and that gives us a leading coefficient of 3. Those two numbers tell us everything we need to know about the curve in terms of what's called its end behavior. Okay? In other words, you know, these polynomials, if we were to graph them, they do a lot of this kind of stuff. Bouncing and turning, and sometimes they look like this, stuff along those lines. And the question we want to know is, there's a bunch of bumps along the way, but can we at least know where it started and where it's going? Where it started and where it's going. This is called the end behavior. On the two ends of the graph, what is it doing? Is it going up or down? And that's something that we want to be able to know about all polynomials. And so generally speaking, if we talk about polynomials in general, there is a way to determine the right-hand side and the left-hand side pretty directly. And the way that we typically do this is we start with the leading coefficient. Okay? The leading coefficient can be one of two things. The leading coefficient, which is this number out here, can either be positive or it can be negative. If it is positive, that implies that the right-hand side should go up. And this should make sense because if something's positive in general, we expect it to go up the hill. Whereas if it's negative, we can assume that the right-hand side will go down. Now this is really important. The leading coefficient, which is the first thing that I'm looking at, tells me about the right-hand side. Not the left, but the right. So in this example here, okay, where I had the degree of 4 and the leading coefficient of 3, I'm going to draw two little lines. These will represent my arrows. Notice I haven't drawn whether they're up or down yet. I just drew the two of them. Okay, the leading coefficient is 3. That is positive. And because it's positive, I know that the arrow on the right will go up. I still don't know anything about the left yet, but I do know that the right arrow must go up. The next thing we look for is the degree. The degree can be one of two things. Because the degree is an exponent, in a polynomial that exponent has to be positive or it's not a polynomial. I know we did a little with negative exponents in 5.1, but our goal is to get positive exponents anyway, and so we're going to look at that. That'll always be positive. So then the question is, how else could I describe this degree? And the answer is it can either be even or it can be odd. Okay? If the degree is even, then the left-hand side is the same as the right-hand side. Meaning that if the right side is up, the left side is up. If the right side is down, the left side is down. And if it's odd, then the left-hand side is not the same as the right-hand side. Meaning that if the right-hand side is up, the left side would be down. So let's come back to our example here. This number 4 is even for my degree, which means the left-hand side must match the right-hand side. And so I know without graphing this polynomial fully that it's going to be up on the left and up on the right. Some sort of a W shape or something like that. And there we go. That's how we know how to produce what's called the in behavior of a graph. And in the homework it talks about infinity, negative infinity, positive. All we're going to look for are those two arrows there. What's the in behavior in terms of the arrows? There's one other part to the assignment that we really need to cover. So let's take a second and clear this screen, give myself a little bit of space. All right. So this last thing that we're going to cover, these last couple of things that we're going to cover, rather, have to do with the concept of substitution. So if I have y equals 3x cubed plus 2x squared minus 5x plus 1, and I want to put, say I want to plug in or find out what happens when x is 2. That traditionally means, and this is what we call direct substitution, that I'm going to have to plug in 2 into this equation in every position. 2 cubed plus 2 times 2 squared minus 5 times 2 plus 1. And now I have to go through my PEMDAS, my order of operations, to clean this up. I'm not going to multiply until my exponents have been done. 2 to the third is 8 plus 2 times 2 to the second is 4 minus, now I can do some multiplications. That's 10 plus 1. This becomes 24 plus 8 minus 10 plus 1. 24 plus 8 is 32. Minus 10 is 22. Plus 1 is 23. Now, that's something that we've known how to do for a long time, and hopefully with PEMDAS we can do a pretty effective job. As a side note, this right here, if we type it exactly the way it looks into a calculator like a TI-84 or Desmos, it'll evaluate it correctly for us and give us a simple answer. We don't have to do the steps individually. That being said, there is another way to do this. It's called synthetic substitution. The reason it's called synthetic is because it looks fake, to be honest. It looks, well, it's man-made for sure. It's something that we created, when I say we, I mean mathematicians created a long time ago to help work with these polynomials. And while today's assignment, you might say, Mr. Welch, I don't know that it helps that much. In the long run, it's going to blow your mind. It's going to be so helpful in future assignments that it's a skill we want to learn now. So we want to really perfect this skill, okay? And the way that it works, we're going to build this little box here like this, all right? And we're going to take just the coefficients of our numbers, of our x terms, and then our constant. So I'm going to take the number 3, positive 2, negative 5, and positive 1. I always want my last number to line up above this little bucket I'm putting down here. This is where my answer is going to be. I can even circle it right now. My answer is going to pop out right there. And then the number that I want to put in, I call it the bouncer because he's the one that lets you into the club, into this little box here. All right, so the first number always adds straight out. There's no number underneath it, so 3 plus nothing is 3. To get back into the club, I have to go through my bouncer over here, so I times by 2. 3 times that 2 is 6. I always add to get out. 2 plus 6 is 8. And if I want to get back into the club, I have to times by 2 again. And 8 times 2 is 16. And if I add a negative 5 to a positive 16, I get 11. And 2 times 11, once again, is 22. And if I add 1 to 22, I get 23. Notice, it's the same answer that we got from doing direct substitution. This synthetic substitution allows us to simply add and multiply repetitively and still get the same answer. With the advent of a calculator, does this really help us? Yes and no. It might not feel the most helpful in this assignment, but it is a game changer in future assignments. And we'll talk about that as we get there. Good luck. Watch the note video or the homework help video if you have some questions on specific problems. Good luck.